are provided with solid F, 2 more hydrochloric acid solution G, 0.1 more sodium hydroxide solution. You are required to determine the enthalpy change of the reaction between solid F and 1 mole of hydrochloric acid. Procedure 1. Using a burette, place 20 centimeters cube of 2 molar hydrochloric acid solution G in 100 beaker. At exactly 2.5 minutes, add all solid F to the acid. Stir the mixture gently with a thermometer. Measure the temperature of the mixture after every half a minute and record the values in the table. Retain the mixture to be used in procedure 2. Very important. So that's why important you need to read it through before you start the experiment so that you cannot mess. If you pour down this solution, then it means you procedure 2 you are going to suffer. So according to this is my temperature. So when you have not added anything, this is the room temperature. In my room temperature, it is 19.0. Always temperature record with 1 decimal place. If it is 20, you write 20.0. If you decide to use 22, you 23.0. So temperature record with 1 decimal point. Now there is this point when the time is 2.5 here at exactly 2.5. This is where we have our X. This is our reference point. Our reference point. So you are going to see how we are going to use this point. And then now from there, after adding the solid F, the temperature will fall. In this case, the temperature will fall 15 from 19 to 15, 15.5 all the way. Plot the graph of temperature against the time. So whenever you are told to draw a graph of temperature against time, or a graph of time against temperature, or a graph of distance against whatever. So this is what I want to explain. This is the y-axis and this is the x-axis. This is the y-axis. So here you need to understand that when to temperature against, the one that comes before the name against is going to be the y-axis. So here we are going to have temperature. Then the name, the whatever that comes after the word against is the x-axis. So this one will be time. So that is the first thing you need to mark because that is what is being marked. So this is temperature against time. Temperature against time. So this is our graph. So you draw the axis, you label the axis as I have told you. So this is how you will label your axis. We will have temperature against time, and then you write the time. I've started at 0. I've started here at 0. And then I have one like that. So this is what is marked, that you have labeled the X and the Y axis, that is labeling. Then after labeling now, you need to put the points. I have given my scale here. I've broken my graph from 0 like this. So I have started at 10 and then I have given 1, 2, 3, 4, 15. So it means my scale inamaanisha 4 small squares is equal to 1. So nikihesabu 1, 2, 3, 4, hiyo ni 11. 5, 6, 7, 8, hiyo ni 12. 9, 10, 11, 12, hiyo ni 13 hivyo mpaka nifike 15. So nikihesabu 15, 19 ni hapa, ndio hii 19. So nimeweka 19 hapa, hapa 19. This is my 19. 19 tunaweka 19, it is a constant mpaka when the time is 2.5, because it is at this time 2.5 where you are going to put the solid. So when the solid was added, the temperature decreased to 15. That was now the 15 I have put here. Then next, 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 next. Now what you do here, you take a ruler and you draw a line, a straight line. You take a ruler and draw a line of best fit. Best fit, line of best fit ni ile line unawe ukishaweka rula hivi, angalia ni zile ni line gani, ni points gani, mali rula inachukua more point, ni wapi inachukua more points. Kwa mfano nikiweka inachukua, nikiwa na point hivi namna hii, so sitaweka rula namna hii, nitaweka rula hivi yenye itachukua hizi points mingi. So you know. Now when you put like that, now you draw this line from here, you draw this line like that, it will be like that one. So you have drawn that. Now you need to know that this, at this point, this is our reference point here. This is our reference point, mahali we have our x. X ilikuwa kwa 2.5. So what you do, you extend this, you extrapolate this line to our reference point. So you extrapolate up to here. Now you read the temperature here. You read the temperature here, and that is the final temperature. That is the final temperature. Now after drawing this, I have drawn out the line. I have drawn the line using the line of best fit. After that, now you extend this line to the reference point. The next thing, I have extended now the line. Now at this point here, now you read what is in the x up the y axis. Now follow, draw a dotted line up to here and read the temperature there, and that is our final temperature. So this line, it is important you draw this line where we have our x. Our x was at 2, so you need to draw that line. That is where we have our x here, and now that is our reference point. Ndio maana tuna extend from this point, tunaweka dotted to our reference point, and that is where we will have the final temperature. This was initial, this is final. So that will help us to get now the difference, the temperature change. Now find the determine the temperature change. Now you see our final temperature is 14.5. Our initial temperature was 19.5, 19.0. So here you don't do like we do in maths at 14.5 minus 19 upate negative 4.5. No, because the only thing this one is telling us, if the initial was 19 and the final is 14, it tells us that the reaction is endothermic. It is only telling us that the reaction is endothermic, therefore the difference is 19.0 minus 14.5, which is 4.5 degrees Celsius. We don't put a negative in temperature because it is only telling us that it is an endothermic reaction. The reaction is endo. So remember, it has shown that the reaction is endothermic. When temperature increases from the initial, if our initial was 34, then the reaction is exothermic. But now since the initial is less than the the final is less than the initial, then the reaction is endothermic. It means that the energy is absorbed into the system and the difference is lightweight. Now next is when calculate the heat change for the reaction, assuming the specific heat capacity of the mixture is this, density of the mixture is that. So we know that heat change is equal to capital M standing for the mass of the solution, capital C specific heat capacity, and temperature change. Now mass that we used 20 centimeters cube, so 20 centimeters cube, you divide, this is the same as 20 gram, you divide by 1,000 to change that into kilograms, and then times specific heat capacity 4.2 times temperature change 4.5. This one will give us 0.378 kilojoules. I want to remind you that capital M is equal to the mass of the solution used. So if you use 20 centimeters cube, remember the density is 1. It means that 1 gram, 1 is equal to 1 centimeters cube. So we will ask 20 centimeters cube itakuwa ngapi? So ni 20 times 1, which is 20 grams. Ndio maana nimeweka 20 grams nikadivide by 1,000 to change into kilograms. That's what I have done. The molar 8 of the reaction between solution T and the molar. So we want now to get the number of moles of what we have provided, but we were given that solution G is 2 capital M. 2 capital M means that the number of moles in our liter is 2 molar. So it means it's 2 moles. So 2 moles is in 1,000 centimeters cube. Now we can find out 20 centimeters cube of solution G will contain how many moles, because that's what we have used. This one will give us 20 times 2, that is 20 times 2 divided by 1,000. This gives us 0.04 moles. So it means the number of moles that was able to produce this 0.37 kilojoules is this. So 0.04 moles was able to produce 0.378 kilojoules. We want to know 1 mole because molar means 1 mole will contain how many? 1 times 0.378 divided by 0.04, and this one will give us 9.45 kilojoule per mole. Now, because our reaction was endothermic, you remember to add the sign here positive, because that is the final thing you remember, because the reaction was endothermic. Thoroughly and fill it with sodium hydroxide. Transfer all of the contents of the beaker from procedure 1 into a 250 volumetric flask. Add distilled water up to the mark. Label the solution H using the pipette and the burette. Using the pipette and the pipette villa. Place 25 cm of solution H into a 250 conical flask. Add 2 to 3 drops of phenolphthalein indicator and hydrate again as sodium hydroxide. Record the salt in the table 2. Repeat the titration 2 times to complete the table. So my volume is 22.5. Initial, always remember to 1 decimal place 0.0, 0.0, 0.0. Now do the subtraction. This one will be 22.5. Remember the decimal point should be consistent. 22.4, 22.5. Now that's what will give you the marks in the table, all of them. So I hope now you are understanding what we are doing. We are bringing the solution, the one that reacted with solid F. We are bringing that solution in the beaker, transfer it into the conical flask, into the volumetric flask, and then top up to 250. So the volume that now the solution we have H, solution H, ni nini, ni HCl, but the difference from the original solution G is that this one is diluted because we have diluted after reacting with solid F. Now the one that was in excess has been diluted to 250, but that one is also HCl. So here, remember now, sodium hydroxide in the burette, therefore the average volume here is for sodium hydroxide. The average volume is for sodium. So what is the average volume? You simply take these ones, 0.5 plus 22.4 plus 22.5, you divide by 3, because the range after the decimal point is less than 0. Is not more than 0.2. Now we can do the average for both, for the three of them. Now this one will give us the average of 22.46 centimeters cube. So you realize this was 22.46666. You truncate 1, 2, 3, 4 significant figure. You truncate. You don't round off. You just truncate. In chemistry, you truncate. Calculate the number of moles of sodium hydroxide used. So to know the number of moles of sodium hydroxide used, you go back to what you are provided with. So here you are provided with 0.1 molar sodium hydroxide. That is the keyword. 0.1 capital M implies the number of moles in 1,000 centimeters cube. You should know that. Now we know that 0.1, it is the number of moles which are in 1 liter. A liter is 1,000 centimeters cube. But what is the volume of sodium hydroxide we have used? It is this, used this. So we will ask 22.46 centimeters cube will be how many moles? 22.46 times 0.1 divided by 1,000. This one will give us 0.002246 moles. That will be the number of moles of sodium hydroxide used. Calculate the number of moles of hydroxide in excess from procedure 1 as reacted with HCl, HCl which was excess from procedure 1. So HCl will react with sodium hydroxide to form sodium chloride plus water. The mole ratio, as you can see here, is 1:1, meaning that is 1:1. Meaning that number of moles of HCl in 25 centimeters cube solution H will be equal to that of sodium hydroxide because the ratio is 1:1. 0.002246 moles is the same because the ratio is 1:1. Now we have the number of moles of solution H in 25. We can get in 250 simply by. So what is the number of moles of H in 250? So we say 25 centimeters cube H contains 0.002246 moles. 250 centimeters cube H will contain how many? That is 250 times 0.002246. You divide by 25. And this one will give us 0.02246 moles. So that is the number of moles in 250. Calculate the number of moles of hydrochloric acid in 20 centimeters cube of solution G. Now solution C is the original solution. Now you need to know that solution G, calculate the number of moles of 20 centimeters of solution G. Solution G, we had told that it was 2 molar. Calculate the number of moles. That one will be 2 capital M, 2 moles of solution G is equal to in 1,000 centimeters cube. Tumetumia 20 centimeters cube, so itakuwa ni 20 times 2 divided by 1,000. So moles in solution 20 will be 0.04 moles. That is the moles in 20 solution G. Now then calculate the number of moles of hydrochloric acid that reacted with solid F. That's very good. Now let us get the number of moles that remained. Moles of G that remained. In 20 centimeters cube. First, moles in 250 centimeters cube solution H in 20 centimeters cube solution G that remained after reacting with solid F. So inamaanisha moles in 20 centimeters cube that remained will be equal to 0.02246 moles, because we have calculated the number of moles in 250 in our previous Roman 3, I guess. Next, now, the number of moles that reacted with solid F is the total, which is 0.04 minus this one, 0.02246, which is equal to 0.01754 moles. Those is the moles that reacted with solid F.